Okay, so last time we did the fundamental theorem of arithmetic. I'm going to use it a lot more. Then we did I actually never stated in the proper way, but this is called the divisor theorem. So in addition to the Euclidean algorithm, with the way it is described, the actual process of the proof. But then you don't really want it carried out every time. It is just a matter of computation, how to find it, right? This is the familiar division by subtraction thing, the Euclidean algorithm. But primarily, all you care about is just having that equation right there. In the middle, divisor dividend, divisor quotient and remainder, so you can always have it written once and for all. You have two numbers, you divide with a remainder, and those two numbers exist. So it is ultimately an existence theory. The fact that is behind it, the proof is what's called constructive. In other words, the number can be found through an algorithm. Okay. So that's a separate issue. The point is that such a representation exists and it is unique. Okay, so that is the remainder theorem. So before I forget, let me just state it here. Okay. Remainder theorem. So carefully writing out the conditions is very important, and so all the caveats have to be there. So nothing can be assumed unless there are some exceptions, but most of the time the theorem itself should be self-contained. So suppose A and B are integers. Oops. Okay. Okay. So what else do we want to require? There is no, for example, there is no restriction on A and B, and having B being smaller than A doesn't have to be the case. So we could just as well divide it, even if they're, even if it's, you can divide a small number by a large number. So what is going to be simply if A is smaller than B, then it simply will be remainder itself. The quotient will be 0. Okay, so because, well, as you can see in a moment. So the only thing that we have to require, so we also suppose B is not equal to 0. So if we want to divide by B, let's assume that it's not equal to 0. Okay. And then what else? Then there are integers Q and R called quotient and remainder, such that A is equal to QB plus R, or larger than or equal to 0, less than B. Okay. I want to make B positive. I want to make B positive, just in case. Okay. And then the second part. So that is the existence. As you can see, this is the existence right there. There are. And then the second one is the uniqueness, as it's frequently the case. So you say furthermore, these numbers Q and R are unique. Okay. Unique. So once again, the two typical statements, parts of a theorem, existence and uniqueness. Existence and uniqueness theorem that we saw was the fundamental theorem. Existence of a factorization, which is also unique in some sense. Okay? So what else? Can you think of other existence uniqueness theorems that you know? Well, one we just got to, and that, but well, it's not exactly a match. Is this one? Well, there's no theorem yet, but when you actually get to it, then there, in order to accommodate the language that we want to use, the limit, you have to deal with that problem early on or right away. And that will be the question of demonstrating that the limit is unique. So there is no as we know, the limit doesn't have to exist. Okay, so that is a part of the problem that you address. So once again, existence and uniqueness, you want to address these two as early as possible. Okay, so it is whenever you introduce a definition, this is the question is this well defined? Well defined is ideally when you have the concept that has been introduced is both unique and exists, and it is unique. Okay, so early on you can look at the existence, and we already know that it does not have to exist. The limit doesn't have to exist. So there is no existence as such. There is no existence theorem unless we impose extra conditions. So that's the rest of calculus. Calculus 1. Okay, that's first existence, and then secondly uniqueness. And uniqueness, yes, it is true, and so it is actually a theorem that goes right up after the theorem. So you don't want to start using the language of the. In fact, I would discourage putting the there. I would say a limit is any number that satisfies this property, but then you use this theorem which justifies the language, and you will be using the limit. So if the limit exists, it's unique. That's the plain language. If a limit exists. Okay. Okay. So that is the uniqueness theorem without existence. You certainly can have theorems that have existence, no uniqueness. For example, maximum points. Well, we'll get to that. We'll do that today. Remember, continuous function on a closed bounded interval has its maximum points. Okay, there might be several, more than one, right? Like this. So there's several, but then the theorem claims existence but does not claim uniqueness. Okay, so we can have one or the other or both, but when we don't have both, then it's probably, well, it happens, but less interesting. So I'm not going to prove it, but the only thing that I want to make is out of this is just to once again look at this with the quantifiers and make sure that we understand what it means. So first of all, the definition, as you can see, a limit is such a number that satisfies this. So for any epsilon, there's an n, such that for any n larger than n, so n is within epsilon from that number L. Okay. Okay, I don't have. Let me finish this theorem first, and then I'll go back to the definition. So the limit exists; it is unique. So how do we state it in the form of a more formal statement, which will, because what is unique exactly? Let's translate what it means. So how the full theorem would be restated as follows. So suppose n is a sequence, okay, and also suppose L is a limit of an, well, so how do you say it's unique?
L is the limit?
What? No, well, no, cart and horse. We are trying to show that we can use the. That is a theory that justifies the. Okay, so right at this point, I'm using a limit. Okay, so it's still possible. So we are building, it's mathematics. We build everything gradually, and we don't make a next step until we make sure that we are safely have proven everything that we're going to rely on. Okay, so how do you remember that from calculus, maybe the statement of anything being unique, and that is limit of sequences, limits of functions, I don't know, the derivative, the integral. So what does it mean it's unique?
That it only has one
Okay.
solution?
What one solution is also same word as unique. Try to go negative here. Can you say turn it negative? There's only one solution. How do you make it negative? There's only one L.
Many solutions?
No, negative. I meant the same statement in the negative sense. In other words, kind of contrapositive, I suppose.
There are no other solutions? Solution less than zero.
No. If there is another solution, then what?
It's false. Not.
What?
It's false.
No. If there is another solution, it's the same. So, m is a limit of an. So I literally assume that there are two. And then, that's the conclusion of the theorem, L is equal to m. Okay? So that's how we address uniqueness. We kind of state it as if there are two possibilities, and then we say, well, it's the same. That's uniqueness.
Almost like squeeze theorem?
Well, let's see. Squeeze theorem starts. It's a condition of this squeeze theorem that require that those two different limits of two different sequences have the same limit. That's the squeeze theorem. Okay, so you that uniqueness of the limit, you could have two. If you have two sequences, you have two limits. Could have two limits. But then you say, well, if it's the same limit, then you have your conclusion of the theorem. So this would conclude that if there is one sequence, the limit could be only one. It's the same limit. Okay. So once again, if you take the same idea and take it to the fundamental theorem of arithmetic, once again, you can say it's unique, and it's kind of that language might be, if you haven't faced it before, it has to be explained, and that's the explanation. So you'd say, well, you have a prime factorization of, say, we have one number. We have one of its prime factorization. We have another of its prime factorization. And then you say that, well, it's the same factorization. In what sense? For every factor here, we have a factor there, and vice versa. So it's pretty much the same set of factors here, same set of factors there. That's uniqueness. Okay? So we'll certainly look into that every time we are stating something about from calculus or elsewhere. So this is very typical situation. Let's take another look at the definition, though. It is complex, so actually it's more complex than the theorem. It's the definition itself. So it has a bunch of parts, and as you can see, we have at least three quantifiers. So let me state it again, and maybe, and then we will just tweak it. Okay, so once again, the definition restated. So let me use more language. At this point, we know that the limit exists, unique. So we don't have to worry about then the language. I could just say L is equal to, and that's I'm just using the notation, and goes to infinity, right? So this is also, by the way, this kind of notation you want to use only after you have justified the uniqueness. because you cannot say that L is equal to the limit when the limit could be two of them. Okay, so you cannot be equal to two things at the same time. So, but now we are okay, because we know that if that thing on the right makes sense to begin with, so there is any answer to that question, then there is only one answer. Okay, so incidentally, the some of the solving equations has it was brought up a minute ago. The question of uniqueness actually is typical in certain places of when you solve equations, and the statement might be if there is a solution, it's unique. For example, if it is a function is linear. So a linear function, and we're looking, so mx plus b is equal to 0. So you know if it crosses the x-axis, there's only one intersection. There can be only one solution, but it's possible there is no solution because the line could be horizontal. Okay, but if it's not horizontal, there is a solution, and that goes all the way with linear algebra. Anybody's taking linear algebra, well, we probably will be taking afterwards. Typically, after this, after Math 300, you take linear algebra. So in high dimension, you have systems of equations, and you have a very frequently similar situation with extra conditions. You can guarantee that the existence of a solution, and then you can also guarantee the uniqueness of the solution. So anyway, we're defining this. We write this when if. I'll put if and only if. Remember, definitions are all if and only if. Okay, so what we're saying here is. Well, let me just write for an epsilon. There is an n. For any n larger than n, an minus L less than epsilon. Okay, so it's very compact, but really scary-looking statement, because as I said, three quantifiers that cannot be interchanged. Okay. So now what trips people up often in this place is the negation. Negation it's important, right? The limit exists, does not exist, and it applies to all the rest of the limits in the calculus, so including derivative and integral. And so what does it mean that the limit does not exist? That is, it sounds like it is a negation, but it's not. Okay, so we know how to negate this statement, right? Well, let's negate this. Remember how we negate? That's a long statement. What do we do to the quantifiers? What? Switch them. So, okay, let's read it. So what am I getting? Switching for any to there is an epsilon greater than 0, such that for any n there is an n lowercase, such that and then we negate the inequality, right? So we just flip the inequality. So an minus L larger than or equal to epsilon. Okay, so very easy. Now it is in fact so easy that you probably have to stop and actually read it to yourself. What is that you're getting? That it makes sense. So if you have an understanding of what the limit is, then you can the negation also will make sense to you if you just read it. But it's harder to figure out from scratch than doing this little algebra, this algebraic trick that we learned. So the meaning of the limit is that if you go far enough by in the sequence, you will be as close. You can bring n as close as you like to L. Okay. So negation is no matter how far you go along the sequence, there will be one, or at least, element which is not close to L as close as we like. Okay. So that's what negation says. So it doesn't mean that all of them are bad. For example, you can have a sequence that looks like this, seemingly conversion, and then I'll just put it like, okay, so that's my sequence. Yeah?
Why do you have to switch the greater than sign after the little n?
Because negation negates, it flips the quantifiers. but then it negates the statement that follows them, which is not exactly the same. I mean, this is a complicated example. You can probably think of a better, a simpler example that does the exact same thing.
Right. But it doesn't flip all the quantifiers?
I did flip all the quantifiers.
On the left side, like the n, the small n is like still greater than the.
Right. Oh, well, an epsilon greater than 0. Right. So that is not flipped.
Okay.
So
Yeah,
it is like an extra condition that we are preserving. Right. So it is only at so it's like a part of the hypothesis of the theorem, and then yeah. So we if we are dealing with only positive epsilons to begin with, we don't want to get out of that category. Let's do that. So why didn't I? That was the question. Why didn't I flip these? I did flip the sign in the last one, but not in the beginning. So let's pick a simpler example that would clarify that, if possible. So I don't know, for every x larger than 0, x plus 1 larger than 0. How about that? Okay, so if I want the negative, I will not touch larger than 0. It's not going to be, so first of all, this statement is true, so the negative will be wrong. So there is an x plus 1 larger than, less than or equal to 0. Okay, so what the point I'm trying to make? So the statement is correct. For any x larger than 0, x plus 1 larger than 0. Okay, so and I'm trying to negate it. So what's the rest of the possibilities? The original statement is saying nothing about negative x's. So its negation should still say nothing about negative x's too. I guess that's the way to see it. I'm not sure if I have a better explanation why you're still preserving a larger than 0 here. Well, there's another explanation. If you half of the time you can restate. Well, those extra conditions, these are in fact can be seen as hypotheses. Let me make it clear with that one. Remember, we can restate. This is how we can restate it as an implication. Okay. So to explain this, why this is true, let me try it. For any x, so what do I do? Plus 0. I snuck in larger than 0 into my preamble. So this is my preamble, and I snuck in a restriction on x into the preamble for convenience, so that we know we don't care about x's that are not positive. But I could bring it inside and make it a hypothesis of it and have an implication. So like this. For any x, now I do not require x to be positive anymore. Then I do this. X is positive, then x plus 1 is positive. Okay? It's the same statement. So this is the same. So for any positive x, x plus 1 is larger than 0. Same statement is for any x. If x is larger than 0, then x plus 1 is positive. You see the same statement, right? Okay, so now let's try to negate this. So we already know that for any x will be here. And then now remember what do we do with implications? Is how do we negate implications? We keep the condition and then show that the conclusion doesn't have to be satisfied necessarily. Okay, so it will be x larger than 0 and x plus 1 less than or equal to 0. So there are two inequalities in the first line there, but they have different places. They are so one is the condition, and the other the conclusion of that implication. So then when you negate, you do negate the conclusion, but not the hypothesis, not the condition. So you can see how it works out that indeed this is negation. X, there is an x such that it is positive, and it is but x plus 1 less than or equal to 0. Okay. So that's the best I can say. It is this reasoning explains why we could always take sort of have an expanded preamble and not have only the quantifiers, but also quantifiers with those little comments, extra restrictions, so that you don't have to list this could be long. Imagine that if I try to apply this idea to the definition right here, then I would have to have it would be a little bit long, so I would have to have for every epsilon there is an n for any n, and then I have here epsilon greater than 0 and n larger than n implies that an minus L less than epsilon. Okay, so that would be a same statement, more cumbersome. So what we then commonly do, we just take epsilon, and wherever epsilon appears, we also introduce restrictions on it. It could be just as well, suppose n is an integer, you'd better say it's an integer in the beginning rather than wait until you are actually starting a proposition. So we sneak it in here. Okay, just careful not to mix up and not, for example, I cannot mention n lowercase until n capital is introduced. By the way, you do remember that example we saw that no interchange of those quantifiers, in order of quantifiers matters, and you cannot flip them. Remember when we talked about that subway situation, and every single one had a different description. Okay, so all right, so that seems to be the way to explain, an okay way to explain that why we do things the way we do. Okay, let's look at the negation. So that's why I brought it up. Is this? So we negated the right-hand side, but what is the meaning of the negation in terms of L and limit? So if I go to the right, so if L is the limit of n, then this long statement. Now we took the negation of the long statement. And now if I go back, how would I describe it in terms of L? Well, the statement is supposed to be equivalent, right? So I just negate the statement on the left. What do I get? L is not the limit, right? That's all. So the common mistake, that's why I brought it up, is actually to say that there is no limit. So the negation of the definition of the limit is not that there is no limit. It says just that number that you're talking about is not it. So it's possible that the limit still exists, it's just a different number. So if you are trying to, at best, if you look at the definition on the right, at best you can do, you pick a specific number, and then you can demonstrate that that number is not the limit. But then it does not prove that there is no limit. So in other words, remember the word is divergence. Okay, so that is why the definition of divergence is, so AN diverges. There is a very simple way to state it: if and only if AN has no limit. Okay, so that's the technical definition of any kind of sequence of functions that diverges, is there is no limit. And then if limit is defined, then you should be able to figure out what this means exactly. But then if you want you're dealing with a specific sequence, then you gotta get to that definition, and then how do I, from the beginning to the end, how do I state it in terms of epsilon? What do I start with? There is no limit, so I could just say that there is no such L. There is no such L. I could say there is, so i.e. There is no such L that, and then followed by the definition that we have. Okay, so it is, however, cumbersome to demonstrate that there is no such L. You would have to, well, I mean, it's not cumbersome. That's exactly how you would be doing it. I just want to put it in the way that is in one logical statement, and it will be so. So what do I start with? There is no such L. So there is no such L that this condition is satisfied. Okay. If you wanted the opposite, if such L exists, then its negation is satisfied. So in other words, for every L, okay, so you don't know if there is no such L is a negative statement that we might try to avoid, but instead let's state it in the positive way. So for every L, the negation of for every L is not the limit. Okay, so I could just go straight to the negation, and I write there is an epsilon greater than 0 for any n. There is an n larger than n, a n minus L larger than or equal to epsilon. Okay, so this is the translation of the definition of divergence. So every L number fails to be a limit of n. Okay, so that's what we're trying to say here. Okay, so just keeping a track of things. Okay, so let's I want to do the same with a few definitions and a few theorems, just sample of calculus. And the next one is, so I don't want to, I'm going to be, the next Fermat's theorem. And I don't want to, which is about derivatives. And I don't want to divide derivative. Derivative, once again, is a limit, so we know how to deal with limits, so that's not a problem by now. Okay, so remember the theorem. Fermat's theorem. What's about? Now let me try to remind you. It's the picture that usually accompanies Fermat's theorem. So what does the picture look like to you? Tangent, yes. So it's going to be about derivatives. Okay. So what's so special about this tangent?
Maximum.
It's a maximum.
So the line
Is
tangent to the curve is horizontal.
that's right. Okay. So that's right. So informally speaking, is indeed if you have a local maximum or minimum, then the tangent is horizontal, but it's really in terms of derivative, because tangent horizontal means derivative is equal to 0. Okay. So the conclusion is f prime of c is equal to 0, and then, as always, we have a problem with the caveats, and this is the punchline. So it's easy to remember the punchline, but then you have to remember the preconditions, and especially you'd appreciate those conditions more when you have to prove the theorem. Okay, so we'll look into that then. Well, maybe not this theorem, the next one. So at some point you have to learn how to prove Fermat's theorem. Okay. So what were the conditions? So there is a function. What's so special about it? Maybe. Well, I mean, continuous where to begin with. So far we're seeing only one point. So this is my C. Well, I don't want to go too deep into trying to remember calculus. Our goal here is just to learn how to not make logical mistakes, and not to try to so inventing theorems is that's the hard part, but at least we want to learn how to write them once we already have the idea. Okay, so the tricky part is then the theorem is when you have to, before you get into the theorem, you have to state the theorem properly. Unless you jump to the proof, that's another option. If you don't remember the exact statement, what requirements are there, try to prove it, and then you start running into conditions that you need. Okay, so if you just look at the conclusion, you immediately realize the function has to be differentiable at C at the very least. Okay, then you have to say maximum also is appropriate. So let me just state it quickly. So suppose C is a local maximum or minimum of y equal f of x, and f is differentiable at x equals c. Okay, then the derivative is equal to 0. Okay, so as you can see, there is the restriction as far as the nice behavior of the function is one single point. The function does not have to be continuous anywhere. It could be continuous everywhere else, but one single limit, which is derivative is, one single limit exists and equal to 0. That's what we are facing. So any particular logic? I don't think we have any particular challenges with the logic of the statement. Okay, C is local, so it involves what? It involves two definitions. The local minimum and local maximum, one, and the second one is the differentiability, and then the derivative as a certain limit. So that's the challenge. So let's make sure that we understand it. Other things, and that is the converse. So then we stated when there is an if and there's a then. So this is an if and this is then. Okay, so we certainly can state converse. But whenever conditions are this complex, there is no one single way to do converse. So let me write it out. Converse is usually this A implies B. The converse, so this is original, and converse is A is implied by B. Okay, but it only works. What about quantifiers? What about quantifiers? You keep them. So the quantifiers do not go away. So then like this. So say for any something, and the A implies B. The converse will be still for any there is, for any there is. Whatever is happening might be a long string of statements, and then A is implied by B. Okay, so nothing changes, but on one hand. On the other hand, we just saw an example when we had the same statement with different quantifiers just a minute ago. See this? Either the definition or the that example about x over here. We could bring some of the limitations on the quantifiers on the quantified quantities such as x being positive. We can bring them in and make them the condition of our implication. There might be none. So once again, if I look over here, there is no what's the converse of that statement at the top? We did negation, so forget about the second line. Second line, converse is not negation, so if I'm asking you to what's the converse of that statement, what would you say? For any x larger than 0, x plus 1 larger than or equal to 0, what's the converse? What? There isn't one because it's not an implication, unless you convert it into implication, which we did right here, right? And then you could convert it. But then again, there is variability. I mean, not in this particular case, but if we look at the definition of the limit again, then there are two restrictions, and I could bring one in and not the other, and then it might appear that it might become an implication in a different way. So that's what we have to do, and then it has to be our judgment as to what exactly to do about it. So let's convert this into into an implication, into A implies B with the caveats or quantifiers in the beginning. Okay, so so the B is clear. That's not going to be changing. B will be still here. That's my B, and A has to be carefully written. You know, in a way that makes sense. So there is for any. Let's list for any function to begin with. So for any f, okay. At this point, I cannot say that f is differentiable. So I could add a condition here: f is differentiable, but I cannot because until c is introduced, it's not working. Okay, so I have to say for any c. And then at this point, I could add the condition that f is differentiable at c, okay? And then, or I add the condition that c is a local maximum or minimum, okay? So, well, let's do the simplest way. Let's take both of these conditions and put them in the, well, let's put them all in. So for any f, for any c, we have three conditions. C is a local maximum minimum of f. Okay, then also f is differentiable. No, that's it. They're just two. Differentiable at x equals c. Okay, and then this statement implies f prime of c is equal to 0. Okay, so that's our statement spread out in a logical way. Okay, so the converse then will simply will exactly the same statement except the arrow is reversed. Okay, so what can you say about the converse?
It's not always true.
Okay. Well, actually, I wanted a more severe criticism here of the statement. Because think about it, the condition of our implication with the derivative is equal to 0 supposed to imply, in part, that f is differentiable, which usually it's supposed to work the other way. So if derivative is defined, then we know it's differentiable, and so as you can see, it's really not very helpful as far as the implication is concerned. It just sticks out, and the relation between saying something about the derivative. You cannot say something about the derivative unless you know that it exists. In other words, already to say this, you already have to assume that f is differentiable. Okay, so with that criticism, as you can see, the converse kind of doesn't make a lot of sense. In order for us to continue, I suggest to take that out and put it here so make it an restriction on the quantifier rather than part of the hypothesis. Okay, so in other words, this is I'm taking this criticism and starting over f for any function f for any c, so that's how you can put it, so that f is differentiable at c. Okay, so that condition then will not be affected, will not be implied by anything. Okay, so that's just a restriction on f and c. Okay. And now I have my implication. So C is a local maximum or minimum of f. Then f prime of c is equal to 0. So that same statement naturally, right? It's the same statement exactly, but now the converse makes more sense, even though it's still not true, but it still makes sense, and sometimes it is true. Okay, so then you would explore further and find out where it is true. So it's not true because you can have derivative equal to 0, even though the maximum, even though it's not a maximum. So the example is, so we have a statement, a candidate for a theorem. Okay, we saying that it's not true. In order to show it's not true, all we need is a counterexample. So what's the counterexample? Derivative equal to 0, it's not a maximum. What does the graph look like? You don't have to remember the formula. What?
Horizontal line.
Horizontal line, it's a kind of worms, just like with is one a prime number or not. So is it a local maximum or is it not? Is it every point is local maximum? Yeah. So no, the standard example, so that he won't have to go into that, is x cubed. Oh, f of x is equal to x cubed, so the graph looks like that. The tangent line is horizontal, but it's not maximum minimum. Okay? So, good thing to remember for further study. Okay, so we say that converse is not true, but at the same time, we might explore it further and ask ourselves, what extra conditions do we need in order to make sure that it is true? So under what circumstances, what extra condition should I impose in order to discard, at least, to discard this counterexample? You also saw it in calculus. So the maximum, local maximum minimum condition or extreme point guarantees the derivative is equal to 0. But not always vice versa, but under certain conditions, having first derivative equal to 0 implies maximum or minimum point. Remember that what that extra condition is? So what else? The tangent line of x cubed is 0. What else is so noticeable about this point?
Switches from concave.
Right. Okay. It is an inflection point, change of concavity. What does it tell you about derivatives? X cubed. It is 0. F double prime is equal to 0. So that's the if we have second differentiability and the function changes the second derivative changes its sign, then you will have an inflection point, and then you do not have a minimum or maximum. But there's a second derivative test which tells you that when the second derivative is not equal to 0, it's positive or negative, you will have an extreme point. Okay, so we'll just do that next time. So f prime of c is equal to 0, f double prime of c is not equal to 0. Okay, something like that. Okay, so we'll just do it next time.